Boom, 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 flash. Okay, so this is gravity practice 2. We're looking at problem 22.6. And what we're looking at here is a Kepler's law problem. So orbital period with orbital distances for a semi-major axis, or possibly a radius if you have a near circular orbit. But we're looking at light, or spectra of light, from a distant G-type star. And what we see using something known as the radial velocity method is that the star is moving in a near circular orbit, and it's just kind of moving back and forth. So we're going to pretend it's a near circular orbit, and essentially the star is moving in a little bit of a circle. Okay, so if here's a star, it's not just stationary. This star is actually moving in a circle. And what could be causing that star to move in a circle? Well, if there was some other celestial body in this star's vicinity, either another star, if you have a binary system, or if what we're really looking for are planets, because we cannot see the planets, they don't shine or emit light. But if there is a planet here, such as another Earth with maybe a different version of you, this Earth will pull on the star just as the star pulls on the Earth. And as this Earth is going around its star, if they're the only two objects in the system, then they're going to go around what's known as a barycenter, or a center of mass of the system. And the star and the Earth will always be on opposite sides of the system here. So when the star, let's say the star is orbiting like this, when the star is down here, that means the Earth will be up here somewhere. And when the star is on the back side, Earth will be over here. And when the star is here, Earth will be underneath. So they're always going to be opposite of each other. And that means that whatever the orbital period of the star here, that is going to also be the orbital period of this unknown planet. Okay? Because the amount of time it takes for the star to go around is the same amount of time it takes for that unknown planet to go around. And that's what we use with the radial velocity method. We look at stars to try to find planets. Now, if the orbital period of the star is 4.6 years, that means the orbital period of the planet is 4.6 years. So we can say t equals 4.6 years. And let's just say, using other astronomical techniques, that we know the mass of this star. We can say the mass of the star is about 1.3 solar masses, or masses of our sun. That's what a solar mass is. So we can say a mass of our sun. And we designate the sun with a circle with a dot in the middle of it. That's Helios right there. We want to know, just based off of this information, the period of the planet and the mass of the star it's going around. Can you figure out how far away this planet is from the sun, or from its star, or its barycenter? What is that orbital radius? And if we thought of this as an ellipse, if this wasn't a perfectly circular orbit, we could say this is like the semi-major axis. That would work as well. But if it's a near circular orbit, we could think about it as just a radius. But a semi-major axis for an ellipse is technically more appropriate. Now, if we look what we have here, we have a period. We're looking for orbital radii, or orbital semi-major axis, and we have masses here. What we can actually use is Kepler's third law to solve this. Kepler's third law, if you recall from prior videos, states that the period squared is equal to 4 pi squared times, for a circular object, a radius, but in general, a semi-major axis of an ellipse cubed, divided by big G, the gravitational constant, 6.67 times 10 to the negative 11, times the mass of the system, which is normally just the mass of the star or the big object. We only really care about everything whenever you're doing very fine point detail work, or if you have like a double star binary. We could run this equation, but what's actually going to be a little bit easier for us is to take this equation and to recognize that because we are in years and solar masses, if we solve for this radius, the semi-major axis, in terms of astronomical units, and if you recall, an astronomical unit is the distance between our Earth and our sun. If we solve for this value in terms of Earth-Sun distances, then this equation down here actually becomes greatly simplified. The equation down here quickly just becomes that the period squared is equal to the semi-major axis cubed divided by the mass of that system, which is really just the mass of the star. But the only thing we need to be aware of here is this period has to be in years, this has to be in astronomical units, and this has to be in solar masses. So since we have everything in years and solar masses, and we can solve for things in astronomical units, it's just a different distance, this problem quickly becomes solvable. We can say that our period, 4.6 years, squared equals a semi-major axis cubed, which is what we're looking for, divided by the mass of our star in this case, which is 1.3 solar masses. Let's multiply the 1.3 to the other side. So this becomes 1.3, and I'm going to start omitting units because the units kind of get weird, but we know they're going to work out in the end, times 4.6 squared, that equals a cubed. And if we want to get rid of this cube up here, we need to take the cube root of each side. And I think the easiest way of writing out a cube root is to take something to that 1/3 power. Because when I take each side to the 1/3 power, well, 3 over 3 is just 1, so I can kind of omit that. So that just gives me a. And then now that's the 1/3 power on the other side. So taking something to a fractional exponent is the same thing as taking some sort of root. And if I take a look at this, I've solved for a. Now I just got to get some numbers. So let's run this through. So 4.6 squared is going to be between 16 and 25. It gives me 21.16 times 1.3 gives me 27.5. So I've got 27.5, and I need to take that to the 1/3 power to equal a. We take things to the 1/3 power on your calculator with that little caret. So it'll be like 27.5. Run the caret, and then we want the 1/3 power. So I'll either put in parentheses 1/3, which is 0.33, or if you feel comfortable actually writing out the fraction, you can say it's just to the 1 divided by 3, and then hit enter. So 27.5 to the parentheses 1 divided by 3. That gives me a value of 3.018. So 3.01, 3.02. And that's in astronomical units because that's an Earth-Sun distance. So it's about 3 times as far away from its star than the Earth is from its sun, or from our sun, which is a kind of cool thing. Quick way to kind of get that information. Now, if we look at part B of this question, what object in our own solar system, so back here, is located at a distance of about 3.01 AUs? Well, the Earth is at 1, so it can't be Earth. If we actually take a look at some of Mars's data, Mars is 2.28 times 10 to the 11th meters away, and the Earth distance is 1.5 times 10 to the 11th. So we get rid of those. 2.28 divided by 1.5 is only about 1.8-ish or something like that. So it's not Mars. If we do the same thing with Jupiter, Jupiter is a distance of 7.78 times 10 to the 11th divided by 1.5 times 10 to the 11th, so the times 10 to the 11th go away. This is about 5.2-ish, I believe. It's like 5.18. So it's not Jupiter. But what's between Mars and Jupiter? Well, that is the asteroid belt. So our asteroid belt is actually located in our solar system about 3 astronomical units away from the sun. And the reason why there's not a planet there is actually due to Jupiter. Jupiter is so massive and is close enough to the asteroid belt that it never really gave the opportunity for those rocky components in that belt to kind of coalesce and form together. That would be a good planet forming region. It would be a good stability zone, except for Jupiter's large massive influence on it, kind of keeping everything and broken up. But yeah, so that's a little Kepler's problem right there. We're once again using Kepler's third law that the period is related to the semi-major axis. But instead of using that complicated 4 pi squared over g, because we're in years, AUs, and solar masses, we have a much simpler equation. And when we run that through, we get our answer down here. Okay? So I hope that gave you another idea of how we can relate things together, and how we can actually use some star data to find other planets with this radial velocity method. But with that, this problem is finished. Why don't y'all take it easy? Have a good one.